Welcome back to Nature Documentary for Sleep. If you enjoy this kind of quiet geography, leave a comment and consider liking and subscribing. Tonight, you're standing on the Deccan Traps, where the ground feels heavy with old heat. It's late Cretaceous India, and the hillside under you is not one rock, but many. Step down the slope, and you can read the plateau like a stack of poured floors. Each basalt sheet has a chilled edge, a broken skin, and the faint seam of a soil that formed in the pause. This isn't a volcano with a mountain and a crater. It's a continent taking repeated, flat impacts of lava. You follow road cuts and escarpments, and the scenery turns into evidence of pulses, plumbing and timing. Somewhere below, Mantle heat is rising, while India is moving north fast enough to change the schedule. So what exact combination of plume pressure, crustal stretching, and fissure opening rates let the lava keep refilling again and again? You think you are standing on stable ground, the kind that exists to hold you up. But this is a memory foam mattress made of stone. It remembers every time it softened, every time it flowed, every time it cooled too fast. The night air in the western Ghats clings to your skin, damp and leaf-scented. You can hear insects working the darkness like tiny engines. And under that noise is a silence that feels pressurized. You crouch beside a road cut where fresh rock is exposed, and the basalt face shines faintly. The surface is not smooth. It is broken into rounded lumps like pillows stacked in a hurry. That texture has a name, pahoeho, and it means the lava once had skin. It cooled on top, stayed liquid underneath, and kept moving anyway. You run your fingers along a glassy edge, and it feels like a bottle shattered by time. That edge is a chilled margin, the place where hot lava met cooler air and panicked. And right above it is a thin red seam, a baked soil that had just enough time to exist. That seam is your first escalation, because it means the eruptions were not one long pour. They arrived, they stopped, life tried to return, and then it got buried again. You straighten up, and the slope ahead becomes a staircase of old catastrophes. Each step is a flow top, and each step down is a descent into another pulse. You take a slow breath through your nose, and you imagine the air when this rock was young. It would not have smelled like wet leaves. It would have smelled like hot metal, sulfur sting, and oceans losing patience. A small stone rolls from under your boot and clinks down to a lower ledge. It sounds ordinary, like any hillside at night, but the ledge it hits is the roof of a lava river that once moved faster than you can run. The first concrete clue is not the thickness, it is the speed implied by the texture. Fast lava makes long sheets, not neat cones. Fast lava needs a fissure, not a pipe. So you stop looking for a mountain-shaped volcano, and you start looking for a wound. You walk along the cut face, and you notice vertical lines slicing through older layers. They look like dark walls inside the basalt, straight and stubborn. Those are dikes, magma that froze in the act of forcing its way upward. They are the plumbing that never made it to the surface. And the fact that there are so many of them means the crust here learned to crack repeatedly. It did not break once, it practiced. You follow one dike with your eyes until it disappears under soil and shrubs. If you could strip the plants away, you would see that these dikes come in swarms, not one fracture, but hundreds, aligned like ribs. That alignment is a direction, and direction means stress. Stress means something was pulling, or something was pushing, or both. You look out into the darkness where the plateau flattens, and you try to picture India as it was, not as a nation on a map, but as a slab of crust, drifting north like a raft. It is moving fast, geologically speaking, fast enough to be rude. The raft is carrying forests, rivers, dinosaurs, and coastlines. And underneath the raft, something deep is rising, slow and hot, like a bruise coming up from within. If the Deccan Traps are the flood, then the bruise is the reservoir. Congratulations, you have to think about the mantle now. You cannot see it, you cannot touch it, and it controls everything anyway. You take another step down, and your boot lands on a flow top that is full of holes, tiny bubbles, frozen in place, like bread that stopped rising. Those vesicles are gas pockets, and they tell you the lava was not just molten rock, it was carrying volatiles, invisible passengers that would later escape into air and sea. You press a fingertip into one cavity, and it feels like a tiny eye staring back. Some cavities are filled with pale minerals, little plugs of quartz and calcite. Those are amygdales, and they formed later when water moved through hot rock and left gifts behind. So even here, in the basalt, you can see time layering itself. First lava, then cooling, then cracking, then water, then minerals, then soil, then plants. That sequence repeats until the repetition becomes the place. A breeze moves up the slope, and for a second, you smell something earthy, iron-rich. The red bowls, those soil layers between flows, have that smell. They are weathering horizons, and they mean rain fell between disasters. Not gentle rain, not romantic rain, but a monsoon pattern trying to do its job. You imagine the sky clearing after an eruption, ash settling, sunlight returning. You imagine ferns and shrubs pushing into fresh volcanic ground, acting optimistic. Then you imagine the ground vibrating again, far away, as a fissure opens. Not a single vent, but a line. A curtain of fire stretching over the horizon. And then the lava arrives, not as a wave, but as a broad, low river that does not care. You realize the stakes of pacing are not academic. If the pulses were close together, ecosystems never recovered, and gases stacked up. If the pulses were spaced out, life got breathing room, and the planet absorbed the shock differently. So you start treating each seam of soil as a timestamp, not a date with a calendar, but a pause you can feel. A pause long enough for weathering. A pause long enough for a thin layer of clay to form. A pause long enough for roots to try. You step down again, and the slope changes under you, becoming blockier. Here the basalt is jointed, fractured into rough columns that break like stacked bricks. Those joints formed as the lava cooled and shrank. Rock contracts when it loses heat, and it does so with quiet violence. It pulls itself apart, and those fractures become future pathways for water, for roots, for erosion, for everything that will dismantle this place later. So even in cooling, the basalt is planning its own ruin. You walk toward a bend where the road cut deepens and the rock face grows taller. The layers are clearer here, each one with its own personality. One is dense and dark, another is more vesicular, another has a rubbly top like broken clinker. That rubbly top is A, and it means the lava was rougher, more churned, different flows, different viscosities, different eruption conditions. And the variety tells you the system was not steady. It surged, it slackened, it changed chemistry, it changed temperature. It behaved like a machine that keeps getting fed, but not evenly. You pause under the highest part of the cut, and the night feels heavier. Above you, the basalt layers lean slightly. Not much, but enough to notice. They tilt toward the coast, toward where the Arabian Sea will be. That tilt is a hint of later uplift and erosion, of the western Ghats becoming an escarpment. But for now, in the late Cretaceous, you are inland from a coastline that is not where you think. India is still an island continent, separated from Asia by ocean. It is sprinting northward, chasing a collision that has not happened yet. That motion matters because it changes what sits above the deep heat. If the heat source is relatively fixed, then India is sliding over it like a conveyor belt. And that means the eruption locus can migrate, pulse, and reorganize. You step away from the road cut and onto a flatter bench where the basalt surface is smoother. Moonlight, or what passes for it through humid haze, makes the rock look oily. You can almost pretend it is still warm, still soft. But then you touch it, and it is cool, indifferent. The warmth you felt earlier was not temperature, it was density, the way basalt holds weight. Basalt is heavier than the granites and gneisses beneath older landscapes. It sits on the crust like a stack of iron plates. And if you stack enough iron plates, the crust responds. It bends, it subsides, it makes room, even if it does not want to. That is another escalation hidden in plain sight. Flood basalts do not just cover land, they load it. They press down. And that pressure can influence where magma goes next. The more you add, the more you change the plumbing. You start to see why this could repeat, not because Earth enjoys repetition, but because cause and effect feeds back. A fissure opens, lava pours, the land flattens, weight increases, stress redistributes, new cracks form at the edges, old cracks reopen, and the next pulse finds an easier path. The landscape is not just a victim, it is part of the mechanism. You walk toward a small gully where water has cut into the bench. In the gully, the basalt is weathered to a soft, dark soil that smears on your fingers. It is the beginning of black cotton soil, the kind that swells when wet and cracks when dry. It is fertile in a way that feels almost unfair given its origin. Life will eventually love this basalt because it breaks down into mineral-rich clay. But tonight, you are not here for agriculture. You are here for the moment when the basalt was fresh and the world was still counting dinosaurs. You look at the gully walls and you see a thin layer of ash or altered material. It is lighter than the basalt, more crumbly. It could be a weathered top, or a distant ashfall, or a chemical boundary. And it reminds you that lava is only one part of the eruption story. Gas and ash travel farther, and they arrive without asking. You feel your throat tighten, just imagining the air during an active pulse. Sulfur dioxide would have mixed with water vapor to make acid rain. Not dramatic movie acid, but enough to stress leaves, to leach nutrients, to corrode shells. Carbon dioxide would have built a longer, slower pressure, warming seas and changing circulation. And all of it would have happened not once, but over and over like a recurring fever. You take a slow step back from the gully and you choose to follow the road instead of the stream bed. It is a simple decision, but it matters because roads follow weakness. They cut where slopes are manageable, where rock breaks predictably. And that means the road is secretly tracing geology for you. You walk along the curve, and the cut face reveals another feature, a horizon of broken rubble, chaotic fragments welded together. It looks like a collapse zone, a surface that was once jagged and then buried. That is the top of a flow that cooled and fractured before the next arrived. The next, lava did not politely settle on a flat surface. It invaded cracks, filled hollows, swallowed rubble, and made it all part of the stack. So the Deccan Traps are not just layers, they are interlocks. Each pulse grabs the last one by the broken edges. That makes the plateau strong, hard to erode, hard to remove. It is why it still dominates the landscape tens of millions of years later. You keep walking, and the night seems to tilt with the land. You can sense the distant drop toward the coastal plain. This escarpment, the Western Ghats, will one day catch monsoon winds and wring them out. It will help shape rainfall patterns across peninsular India. But in the late Cretaceous, even before the Ghats are fully carved, the relief is starting. Basalt piles up, the crust bends, and uplift happens elsewhere in response. Isostasy, that slow balancing act, is already in motion. It sounds like a careful accounting term, and it is. The crust keeps its books over millions of years. Add mass here, it sinks. Remove mass there, it rises. Nothing stays paid off for long. You stop again at a wider clearing where the road has been blasted deeper. The exposed basalt wall is taller than a house, and it has a distinct banded look. Flow interiors are massive, dark, and fine-grained. Flow tops are vesicular, rubbly, sometimes reddish from oxidation. Between them, the bowl layers smear like thin rust-colored frosting. And now you can count, not precisely, but meaningfully. 1, 2, 3, 4, a sequence of individual events. Each one was an eruption you would have heard from far away. Each one would have lit the horizon. Each one would have changed rivers, killed forests, and then cooled into quiet stone. You realize the plateau is a calendar, and you are reading it in reverse. The lower flows are older, the higher flows are younger, and somewhere up there in the younger part of the stack is the timing that brushes against the end of the Cretaceous. That is the larger stake, the one you cannot ignore. The Deccan Eruptions are close in time to a mass extinction. And the question is not just how the lava kept refilling, it is what the refilling did to everything breathing above it. A distant thunder rolls. Or maybe it is only your imagination. But you let it be thunder because it fits the mood. This climate is humid, storm-prone, and sensitive to aerosols. If you inject sulfur into this sky, you change the clouds. If you change the clouds, you change the rains. If you change the rains, you change the soils and rivers and food webs. So when you see those pauses, those soil seams, you stop thinking of them as peaceful breaks. You start thinking of them as recovery windows. And you start worrying about how long the windows stayed open. You move closer to the wall again, and you spot a small lens of sediment trapped between flows. A pocket of sand and silt preserved like a note stuffed between pages. That sediment means there was a brief landscape here. A surface that had drainage, maybe a pond, maybe a sluggish stream. Then lava came back and sealed it. Now the sediment is trapped, protected, and quietly telling you the surface did not stay molten forever. It had time to organize itself. Time for water to move. Time for life to show up again, probably cautiously. You imagine small creatures returning first, insects and burrowers. You imagine plants taking advantage of mineral fresh ground. And then you imagine the ground splitting open again along a fissure line. No warning siren, no evacuation plan, just a long crack and a rising glow. The lava would have come not from a point, but from a seam. That is what makes flood basalts so unsettling. There is no single mountain to blame. The earth itself becomes the vent. You stand there long enough to realize the seam is not a metaphor. It is an engineering choice the planet keeps making because it works. A point vent clogs, collapses, builds a cone, and strangles itself with its own success. A fissure just opens wider. It gives the magma a longer doorway, and it spreads the pressure out like bad news. So you stop looking up for a summit, and you start looking sideways for alignment. You let your eyes follow the terrace edges and the subtle tilts and the repeating benches. Those benches are where flows slowed, cooled, and left a lip. Those lips, stacked, are the stairs you are standing on. And once you see stairs, you start asking what built the staircase factory. Not the lava, not yet, but the heat source that kept refilling the system. You kneel again and press your palm to the basalt. It is cool now, but it feels dense in a way your bones understand. Basalt is what you get when the mantle manages to speak in public. Most of the time, mantle rock stays private, deep, and politely out of your life. Tonight, it is in your face, under your boots, pretending to be ordinary ground. You shift your weight and imagine the crust beneath you as a lid, a thick, stubborn lid sitting on a pot that never turns off. The pot does not boil like water because rock is dramatic, not convenient. Rock creeps, it slumps, it flows so slowly you would swear it is still. But if you wait long enough, the mantle is a weather system. Hot material rises, cool material sinks, and the whole planet stirs itself. Close your eyes and picture the slow churn, like a lava lamp in a waiting room. Not soothing exactly, but patient. Now picture one area of that churn getting extra hot, hotter than the surrounding mantle, more buoyant, more eager to rise. This is where the word plume enters the story, like a suspect in a quiet crime. A mantle plume is not a pipe you can point to. It is a region of upwelling heat, and heat loves to expand. Expanded rock becomes slightly less dense, and the planet notices. It starts to rise, not fast, but relentlessly, like a bruise swelling under skin. You are still on the hillside in the western Ghats, but you let your mind sink down past roots of ancient crust down past the oldest hard core of India, down into the Mantle, where pressure is not a feeling, it is a law. Down where rock holds itself together by force of habit and weight. Here, the temperature is high enough to make stone behave badly, not fully liquid, not neatly solid, but willing to deform. It is the kind of place where time does the heavy lifting. The Plume, if it is here, is a broad upwelling, not a neat spear. And that matters because the Deccan is not a neat volcano. It is a province of lava, an entire region paved in episodes. To feed that, you need volume, and volume does not come from a small problem. You imagine the Plume head approaching the base of the lithosphere. The lithosphere is the planet's outer shell, the brittle part you live on. It is thick enough to feel eternal and thin enough to crack. When the hot Plume head reaches it, the story changes shape. It cannot rise freely anymore, so it spreads sideways, like dough hitting a countertop, flattening outward in all directions. This is the moment where a hidden thing becomes a wide thing. And wide heat does not need one vent. Wide heat can find every weakness, every old fracture, every stressed seam. You feel the scale shift in your chest because it is not personal. It is not one mountain threatening one valley. It is a whole crustal plate being warmed from below and softened and pressured. Congratulations, you are now a lid on a pressure cooker. The good news is the lid is thick. The bad news is heat does not negotiate. Heat accumulates and pressure looks for exits, and the exits are cracks. You can translate this into something mundane because your brain likes that. Imagine thick paint on a wall and a blister forming underneath. The blister spreads, lifts, stresses the paint. Then, at the weakest point, the paint tears. Now replace the paint with continental crust and replace the blister with mantle. It is less domestic and more terminal, but the idea holds. As the Plume head pancakes out, it warms the base of the lithosphere. Warm rock requires less convincing to melt. You do not melt the whole mantle. You only melt a fraction. A few percent melting is enough to make obscene amounts of magma, because a few percent of a continent-sized region is still a continent-sized problem. The magma that forms here is basaltic, low in silica, runny when it erupts. This is why it makes sheets instead of sticky domes. This is why it travels like a river rather than piling like toothpaste. But magma does not just appear and politely leave. It collects. It pools at the boundary where rock changes strength. It waits in sills and lenses and temporary chambers. And waiting magma does what all waiting things do. It looks for the easiest way out. You let your mind rise again, back toward the surface. Back to the dikes you saw cutting through flows like dark ribs. Those dikes are the frozen record of escape attempts. Some succeeded, some failed, and the failures stayed behind as walls. If you could see the whole province from below, it would look like plumbing, a network of fractures, some parallel, some branching, some cutting across older structures. Not a single straw, but a cracked ceiling, dripping magma in pulses. This is where the moving raft of India becomes important again, because the Plume, if it exists, is relatively fixed in the mantle frame. And India is not fixed. India is sprinting north across the ancient ocean, like it is late for a collision. So the hot spot in the mantle stays roughly put, while the plate slides over it. That makes the heat source feel like a blowtorch under a conveyor belt, a stationary burner, a moving crust, and a trail of consequences. You have seen this kind of story in the ocean, in island chains. Hawaii is the famous example, a string of volcanic islands on moving oceanic crust. But here, it is not islands. Here, it is a continent. Continental crust is thicker, more complicated, more reluctant to melt directly. So the plume does not simply punch through cleanly. It heats, it flexes, it stresses, it encourages cracks. It creates conditions, not just eruptions. And conditions can last for a long time. Long enough for pulses, pauses, and repeated burial. You are still standing on a quiet bench of basalt, but in your head, the ground is warming from below. The lithosphere is doming slightly, swelling over the plume head. Doming sounds gentle, like a hill forming, but dome the crust, and you change gravity's rules on rivers. You tilt drainage, reroute water, and stretch the surface. Stretching creates fractures, and fractures become pathways. And this is where the system stops being purely thermal. It becomes tectonic, because stress decides where the first big cracks will open. India is moving north, but it is not moving alone. It carries internal weaknesses, old sutures, old rifts, old scars. The crust remembers every insult, even if it healed. When new stress arrives, old wounds reopen. You walk again along the road, letting it lead you like a lazy guide. Road cuts keep showing you the same theme: vertical intrusions, repeated horizons. You start to see that the Deccan was not born in a single moment. It was built by a system that learned. A crack opened, magma rose, the crust adjusted. Then the next crack opened more easily, because the crust was already tired. The plume head provides the budget, but the crust provides the schedule. And the schedule matters, because life lives in the gaps. You stop at another exposure where the dike is thicker and the contact is sharp. The basalt on either side is older, layered, already part of the stack. The dike cuts through like a late thought, an intrusion after the fact. That tells you the plumbing stayed active even between major surface floods. Magma was still trying, still probing, still pressurizing. Sometimes it reached the surface, sometimes it froze below. Either way, it changed the rock around it. Heat bakes the walls, alters minerals, drives off water. Even a failed intrusion can weaken the crust for the next attempt. So you start thinking in feedback loops again. Heat makes magma. Magma makes intrusions. Intrusions make weakness. Weakness makes eruptions easier. The landscape you see, the staircase, is the surface expression of that loop, but you still need the trigger that turns pressure into a running crack. Because even a stressed crust does not always unzip. It can hold for a while like a jaw clenched in silence. The fissure needs to propagate. It needs to learn to run. And that brings you to the rifts. Not the dramatic ocean-forming kind. Not yet, but the stretched zones in western India. Ancient lineaments, inherited faults, trends that predate this whole flood. They are subtle on the surface, but obvious to the rock. The rock breaks more easily along them. like fabric tearing along a weave. You follow the idea of these trends as if they are roads under the soil, because in a way, they are. They are preferred directions for failure. And failure, here, is the method. Imagine the crust being stretched just a little, pulled by regional tectonics, maybe related to old rifting near the western margin, maybe internal adjustment as India moves. The exact cause is a debate you can hear in distant conference rooms, but you can feel the consequence under your boots. A stretched crust is a cracked crust in training. The mantle plume adds heat and buoyancy, raising the pressure from below. Now you have tension above, pressure below. The crust is being asked to do two opposite things at once. It responds the way stone always responds eventually. It breaks, not with one explosion, but with a fracture that lengthens. A dike begins as a crack filled with magma. Magma is a bully. It pushes the crack wider as it rises. It is buoyant compared to surrounding rock, so it wants to go up. As it rises, the pressure at the tip concentrates. That tip can split rock ahead of it, extending the fracture. So the dike grows upward and sideways, a blade forced through the crust. This is what it means for cracks to learn to run. Once a dike finds the right stress field, it can propagate for tens of kilometers. Not in a single instant, but fast enough to be terrifying. The surface expression is a fissure eruption, a line of vents opening nearly at once. A curtain of fire, not poetic, just accurate. And the first major pulse of Deccan flood basalt is that curtain becoming a river. You pick a crack in your mind, one that finally reaches daylight. You stand beside it, late Cretaceous air thick and wrong. The ground trembles with the low-frequency insistence of rising magma. Then the surface splits, not neatly, but decisively. A line opens, steaming, spitting gas glowing from within. At first, it is just gas and heat, a promise. Then the basalt appears, dark red, fluid, moving. It does not leap upward into a towering column. It spills. It pours out like an industrial accident with no off switch. The lava spreads thin because it is runny, because it is hot, because it is supplied. It forms a sheet, a broad front advancing with quiet speed. You can run from a point lava flow if you are lucky and rational. A sheet flow is different. It does not chase you from behind. It surrounds you from multiple directions. It fills low ground first, because gravity has opinions. Valleys disappear, not with drama, but with coverage. Rivers hiss and vanish under steam and sudden stone. Forests ignite where the heat is high enough and suffocate where it is not. Animals run until they find the next sheet, and then they stop being animals. The first pulse builds a floor, not a cone, not a mountain, but a new base level for everything. And that new floor changes what the next pulse will do, because the next pulse will not find the old valleys. It will find a flatter world. A flatter world lets lava travel farther because there are fewer barriers. So each eruption, paradoxically, prepares the land for wider flooding later. You begin to understand how a province grows, not by a single enormous flow alone, but by a series of flows that optimize the surface, fill the lows, reduce the relief, remove the obstacles. Then the next lava river can glide. It can spread, thin, cool, and still cover enormous distance. You can see the evidence of this in the flow interiors you touched. Massive centers, chilled margins, vesicular tops, each one a frozen hydraulics lesson. Some flows inflated, meaning the surface crust hardened, while molten lava kept feeding underneath. The flow thickened like bread rising in an oven, except it is basalt. The top fractures into polygons as it cools, making joints that will one day look like architecture. But right now, in the moment, it is a skin forming over liquid. You step back mentally as the first pulse wanes. Maybe the fissure closes, or the pressure drops, or the supply shifts elsewhere. The lava stops coming, and the red glow fades to black. Steam stops screaming, and the air is thick with sulfur and ash. The new rock radiates heat for weeks, months, longer in thicker places. Then it cools enough for rain to touch it without instantly becoming violence. And the monsoon, because it does not care, returns. Rain hits fresh basalt and begins the slow work of chemistry. Water reacts with minerals, pulling ions free, making clays. The top weathers, turning reddish where iron oxidizes. A thin soil forms, not because it is safe, but because life is stubborn. Seeds arrive on wind. Spores arrive on air currents. Insects arrive because they always do. A green film spreads in sheltered spots. You can almost believe the catastrophe is over. Then the ground starts to tremble again. Because the pauses are not mercy, they are pacing. The mantle is still hot. The plumbing is still pressurized. And the crust, now fractured and altered, is even more willing to fail. A new dike intrudes somewhere else, maybe along the same trend, maybe nearby. It exploits a weakness created by the last pulse, or an older fault reawakened. The fissure opens again, and the second pulse arrives. It pours over a landscape that is already flattened, already loaded, already changed. It buries the thin soil, bakes it into a red bowl seam, and moves on. This is how you get the layer cake. Not by one long eruption, but by repeated events separated by just enough time to leave a scar. You keep thinking about those seams now, because each seam is a pause, and each pause has consequences. During pauses, gases lingering in the atmosphere can settle out. Oceans can absorb some CO2. At a cost, plants can attempt recovery if temperatures and rain allow. But during pauses, the magma system also reorganizes. Pressure rebuilds, pathways change, dikes cool and contract. The next pulse may find a different route, or a faster route, or a more efficient route. So the machine does not simply repeat, it evolves. You stand up from the road cut and look out into the dark again. You imagine the fissure lines across the province, some active, some dormant, all potential. You imagine the dike swarms below, radiating outward like black roots. If you could see them in map view, they would form patterns that hint at central stress. A plume head below, a radiating fracture field above, and India sliding north, making the interaction a moving target. That motion can make pulses migrate over time. Eruptions may start in one area, then shift as the plate moves, like a conveyor belt carrying crust over the hottest part, changing where melting is strongest. You can almost feel the plate moving under you, not tonight, but in principle. 1 inch per year sounds like nothing, but give it 1,000,000 years and it is a continent length. Give it a few million and the eruption locus shifts across a subcontinent. So the Deccan is not one spot, it is a zone of repeated failure, migrating, pulsing, stacking. The first pulses build floors, later pulses build the staircase, and the staircase is what you are walking now, millions of years later, as evidence. You walk farther along the bench, away from the highest cut. The air cools slightly, and you hear water somewhere lower, running over rock. That sound, in this story, is never neutral. Water is the auditor that arrives after the spending spree. But for now, the main account is still being filled by lava. You remember the vesicles you touched, the gas, bubbles frozen in stone. You remember the amygdales, minerals deposited later by groundwater. Those are not just textures, they are pathways. Bubbles create porosity, and porosity becomes a hiding place for water. Cracks from cooling create fractures, and fractures become highways for fluids. So each flow is not only a layer, it is a sponge and a sieve. That matters for the future when humans drill wells and call it luck. But it also mattered then because water interacting with hot basalt changes chemistry. It can trap some gases in minerals or release others. It can drive hydrothermal circulation that alters rock and creates weak zones. Weak zones are where the next dikes like to go. Again, feedback, again the system learning. You stop at a place where the basalt top is broken into loose blocks. The blocks are angular, not rounded. This is not river gravel, it is cooling rubble. A flow top that shattered as it cooled, then sat exposed. When the next lava arrived, it flowed over this rubble like syrup over ice. It filled gaps, welded fragments, and made a rough contact. This kind of surface makes it easier for the next flow to grip. It makes the stack more resistant to sliding. It is one reason the plateau stays coherent, and it is one reason erosion later has to work so hard. But you are still back in the late Cretaceous in your imagination. You are watching pulses come and go. The pauses are short enough that the ground stays warm in places you cannot see. Warm rock does not behave like cold rock. It bends more easily and it fractures with less persuasion. So every lull between flows is not just recovery for forests. It is recovery for the plumbing too. Down in the crust, the last dike has cooled and contracted and pulled away from its walls. That shrinkage leaves little gaps, and little gaps become future weaknesses. Magma loves weaknesses the way water loves a crack in concrete. It does not need a new idea, it just needs an old mistake. You follow that thought down into the dark underworld of the province. You are not walking anymore, you are sinking through rock that still remembers heat. First, you pass the stacked flows you already know, each one a frozen riverbed. Then you pass the older basement, tougher metamorphic rock that resents being used. It is full of ancient scars, folded and healed, like a knuckle that never set right. Those scars are not visible from the surface, but stress can feel them, and magma can taste them. You drift deeper toward where the dikes start as hairline fractures. At this depth, the crack does not look like a canyon. It looks like a thin promise, a line of weakness in a wall of pressure. Now, give it magma. Give it a fluid that is hot, buoyant, and under more pressure than your mind likes. It wedges itself in, and the fracture opens like a zipper. This is not one dramatic rip. It is a running tear, advancing step by step. Guided by the stress field, you can almost hear it, a quiet snapping, like ice fracturing on a lake, except the lake is stone, and the ice is your continent. Above, the surface has no idea yet. You are standing in humid darkness, listening to insects, pretending this is calm. But below, the dike tip is climbing, splitting the crust ahead of it. The crack wants to go where the pressure is lower. That usually means upward. Sometimes it means sideways first, looking for a better route. It is like a thief testing doors, except the thief is molten rock, and then, suddenly, it finds daylight, not a point, a line, a seam that opens in multiple places, like the planet yawning open along a fault. Gas escapes first, because gas always runs ahead of liquid. It hisses out, carrying sulfur stink and heat you can feel in your teeth. Then the lava arrives, low and urgent, spilling out in a glowing sheet. The fissure is not a single mouth. It is a row of mouths, each one feeding the same spreading flood. Congratulations, you have discovered the least convenient kind of volcano. You do not get one direction to flee. You get choices, and all of them are wrong. The lava spreads into low ground because it is heavy and obedient to gravity. It does not need to be fast to be inescapable. It just needs to be broad, and it is broad. It drapes over the land like hot fabric, conforming to every dip and ridge. It is so fluid that it can form little channels, little braided streams of fire. Some of it crusts over quickly, forming a dark skin that crackles. Under that skin, the interior stays molten, insulated by its own cooled body. That is how a lava flow travels far without cooling. It is self-packaged. You watch it inflate in places, lifting its crust like bread rising. The roof wrinkles, buckles, then breaks, revealing fresh glow beneath. These are the textures you will touch millions of years later. Right now they are alive, and they are busy erasing a landscape. The flow front advances, and it is not a cliff of lava. It is a creeping edge, a lobe that pushes forward and spills over itself. It is patient, and that patience is what makes it terrifying. It can keep coming for days, weeks longer, because the fissure keeps feeding it. You feel the air changing as the eruption continues, not just warmer, heavier. The humidity turns into a chemical dampness, the kind that makes your eyes sting. Sulfur dioxide is not dramatic when it leaves the vent. It becomes dramatic when it meets water. It turns into sulfuric acid in clouds and rain. And then the rain comes back down. The first drops hit leaves, and you can almost hear the plants flinch. The drops hit bare basalt, and they hiss off as steam. The sky is still dark, but the horizon glows with a low red band. It looks like sunrise that forgot to lift. The eruption is not blasting ash into the stratosphere like a tall explosive volcano. It is exhaling continuously into the lower atmosphere. That matters because the gases do not need an explosion to spread. They just need time and wind and repetition, and you have provided all three. Now the pulse wanes. The fissure quiets not because the system is done, but because the pressure has shifted. The lava on the surface continues to move for a while, then slows, then locks. It cools from the top down, making a crust that thickens day by day. Inside, the last molten pockets find pathways draining out through tubes. Where a tube empties, the roof can collapse, leaving a trench like a wound scar. You will call it a lava tube skylight later. For now, it is a reminder that even cooling lava has plumbing. Weeks pass, months pass, rain returns, because this is a monsoon world, and weather does not take hints. The rain hits new rock and starts tearing it apart chemically. Basalt is rich in magnesium and iron, and it weathers into clays that hold water. The first soil is thin, patchy, and hopeful. It forms where water pools, where dust collects, where microbial life can cling. In sheltered spots, green returns, ferns, primitive shrubs, things that do not need much. Some animals wander back, cautious and hungry. They find a new flatness, a new drainage pattern, a new set of dangers. This is the pause you have been reading as a red bowl seam. It feels like a breath, but it is also a loading phase, because down below, the plume does not stop supplying heat. Melt still forms at depth, still rises into staging areas, still pressurizes cracks. The crust above is now heavier because you have added another basalt sheet. That extra weight presses down, increasing pressure in the shallow crust. It can actually make it harder for magma to erupt in some spots. So the magma looks elsewhere, toward the edges, toward zones of lower pressure. The system migrates, not out of creativity, but out of physics. This is how a province grows outward, not just stacking up, but spreading. And the plate is still moving north, dragging this entire experiment across the mantle. So now you have several clocks running at once. A thermal clock, heat rising and melting rock. A tectonic clock, stresses stretching the crust and reactivating old faults. A loading clock, each new flow-changing pressure fields. And a climate clock, gases accumulating and dispersing between pulses. The pulses are not random. They are the surface rhythm of these clocks interfering with each other. Sometimes they line up. When they line up, you get a big episode. When they do not, you get a pause that feels like mercy. But mercy is not what is happening. You are just watching a machine cycle. So you move with it, following the next crack before it breaks. You drift eastward across the imagined province, where the crust is slightly higher. Here, the land is not yet buried under as many flows. The old landscape still has some shape, some valleys and ridges. And you can feel the tension building because the crust here is being flexed. Demang over the plume head lifts the surface slightly. Lift it, and you stretch it like a drum skin. A stretched drum skin cracks if you push from below. Now the push comes. A new dike starts. Deeper down, a blade of magma forcing its way upward. It follows an old lineament, a structural grain in the crust. It does not care that the lineament formed hundreds of millions of years ago. It only cares that it is weaker than its neighbors. You follow the dike as it propagates. It is not a smooth journey. Sometimes it stalls, cooling at the tip. Sometimes it branches, sending offshoots into smaller fractures. Sometimes it hits a tougher layer and deflects sideways. But the pressure keeps building behind it. And behind pressure is supply. Eventually, it finds the right route. The crack reaches the surface, and the ground splits open again. This time, the eruption happens on a landscape already altered by previous flows. There are fewer deep valleys to trap the lava. So, the lava spreads wider, thinner, farther. It forms a sheet that can travel across tens of kilometers, even more, before it cools. It floods lowlands, but now the lowlands are different. They were filled before, and now they are just shallow dips. So the lava becomes a painter, spreading an even coat. This is why flood basalts can cover absurd areas. They make their own flatness, then exploit it. You watch the sheet cool, then crack, then join the growing staircase. And as it cools, it releases gases again, not just from the vent, but from the lava itself. Gas bubbles rise through the molten interior, then freeze as vesicles near the top. Some gases escape into the air. Some stay trapped until later, when groundwater finds them and reacts. But the atmosphere receives its share either way. Now you stop following the lava and start following the invisible part. You track the gases because they are the part that can reach beyond the province. A lava flow kills locally, brutally, then stops. Gas can haunt the entire planet. You stand downwind of the fissure where the glow makes the horizon look bruised. The air tastes like pennies and burnt matches. Your throat tightens, not from smoke alone, but from sulfur dioxide irritating wet tissue. Your eyes water, not from emotion, but from chemistry. Above you, the plume of gases hugs the lower sky. It mixes with monsoon moisture and begins making new compounds. Sulfate aerosols form, tiny particles that reflect sunlight. That reflection cools the surface temporarily, like a thin veil thrown over a lamp. But at the same time, CO2 is being added too. CO2 does not reflect sunlight. It traps heat. It stays longer, working slowly, like an invoice that keeps accruing interest. So you get a climate tug of war. Short-term cooling, pulses from sulfur haze, longer-term warming from greenhouse loading, and in between, chaos. Rainfall patterns shift because monsoons are sensitive to temperature gradients. Change land temperature relative to ocean temperature, and you change winds. Change winds, and you move moisture to different places. Some regions flood more, some dry out. Plants do not like uncertainty. Neither do oceans. You follow the sulfur as it rises, carried upward by hot convection and storm systems. In the upper atmosphere, sulfate aerosols spread further, whitening the sky. Sunlight becomes dimmer, more diffuse, like morning through a dirty window. Photosynthesis slows slightly, not because life stops, but because it is being taxed. Now follow the rain. Acid rain falls downwind, and it does not melt you. It just leaches soils, strips nutrients, stresses leaves, and dissolves carbonate shells in shallow seas. It makes ecosystems work harder for the same result. And ecosystems already have their hands full because the late Cretaceous is warm. Sea level is high. Shallow seas cover large parts of continents, turning coastlines into broad shelves. Those shelves are nurseries for marine life, but they are also vulnerable to chemistry changes. Now add CO2 to the ocean. Some of it dissolves into seawater, forming carbonic acid that lowers pH. which is a polite way of saying it makes the ocean more corrosive. Coral reefs struggle. Plankton, with carbonate shells, struggle. And plankton are not just tiny things you ignore. They are the base of marine food webs. So you are watching the bottom of the pyramid get sanded down. Meanwhile, basalt eruptions can also release halogens, like chlorine and fluorine compounds. These can attack ozone in the stratosphere, thinning the shield that filters ultraviolet light. So while sunlight is dimmed by aerosols, the ultraviolet component can become harsher at times. It is an irritating combination, like being cold and sunburned simultaneously. Congratulations, you have invented a climate that cannot decide how to hurt you. Now you feel the repetition again. The eruption is not one season of misery. It is multiple pulses over tens of thousands of years, perhaps longer. Each pulse injects gases. Then there is a pause. During the pause, aerosols settle out in a few years, and the sky clears. But the CO2 remains, lingering, warming, changing oceans. Then another pulse adds more sulfur, more haze, another short cooling. The climate jerks back and forth, like a thermostat controlled by a bored child. Life can adapt to stable hardship. It struggles with oscillation, because oscillation breaks timing. Migration, breeding, flowering, ocean upwelling, all of it depends on seasonal cues. Change the cues too often, and you create a world where the rules keep shifting. You stand at the edge of a shallow inland sea. Somewhere on this moving Indian raft, the water is warm, almost bath temperature. It smells faintly of salt and decay, because warm water holds less oxygen. Now imagine oxygen dropping further, because warming reduces mixing. Stratification increases, the surface stays warm, the deep stays isolated. Organic matter sinks and decays, consuming oxygen. Eventually you get hypoxia, low oxygen zones. In the worst cases, anoxia, no oxygen at all. Those zones are dead layers in the sea, places where fish cannot go. And if anoxic waters spread, you get die-offs and black shales forming on the seafloor. This is not a theory you have to take on faith. Rocks preserve these signals. Carbon isotopes shift when the carbon cycle is disrupted. Mercury spikes can indicate volcanic emissions. Sediments record stress in microfossils, in reef collapses, in extinction pulses. So while you are standing in the haze, coughing quietly, the planet is also writing receipts. Now you return to land, because land is where the flood basalt is doing its most obvious work. Forests near the fissures are gone, burned, or buried. But even far away, forests are stressed by acid rain and climate swings. Leaves show damage, soils lose nutrients, insects and herbivores are affected. Then, predators. Food webs are not fragile like glass. They are fragile like a balancing act. You can keep them going until you cannot, and the repetition is what pushes them. Each pulse arrives before full recovery. Each pause is shorter than the time needed to rebuild complexity. So the biosphere becomes tired. Not dead, not yet, but fatigued. A tired biosphere can survive a lot, but it cannot survive everything at once. And this is the part where your timeline starts tightening. You are approaching the late Maastrichtian, the last chapter of the Cretaceous. Dinosaurs still walk this land, but they are walking under an increasingly unsettled sky. Sea level is still high, but circulation is changing, and the Deccan pulses are either beginning to intensify or at least becoming frequent enough to matter. Here is the delayed question you cannot avoid. Are these eruptions alone enough to tip the world into a mass extinction? Or are they the weakening agent, the slow poison, the sleepless stress that makes the planet vulnerable to something else? Because there is always something else. Earth does not like single causes. Earth likes dog piles. So you listen, not to the lava, but to the silence between pulses. In that silence, the sky clears for a while. Stars return, faintly, through humid air. Rain becomes normal again. For a few years, maybe decades. Life takes advantage because it has no choice. You can almost believe stability is coming back, but the rock beneath you does not care what you believe. Below, magma continues to pool, pressurize, and prepare. Below that, the plume keeps rising heat into the system. And above, in space, a different kind of inevitability is approaching. You do not see it yet. No comet tail, no bright omen, just a normal night sky, full of indifferent light. But a large asteroid is on its way, and it is not going to negotiate with your volcanic schedule. For now, you stay in the volcanic world because the impact is not here yet. You are still tracking the way gases move and stack. You follow winds across the tropics because India is still at a relatively low latitude. Warm oceans feed strong evaporation. Strong evaporation feeds storms. Storms loft aerosols and redistribute them. So Deccan emissions do not stay local. They move through the global circulation, especially if eruptions are frequent. And that means other continents feel the stress too. Not lava, but climate. Aerosols can cool the surface and weaken monsoon systems elsewhere. CO2 can warm oceans and intensify some rainfall while drying other regions. The late Cretaceous is already a greenhouse-leaning world. Add more greenhouse gas, and you push it. But the sulfur does not let it be a simple push. It becomes a lurch, a stumble, a fever that alternates chills and sweats. Now consider wildfires. Volcanic lightning along fissure curtains can ignite vegetation. Dry periods can make forests more flammable. Ash can blanket leaves and reduce photosynthesis. In some areas, you get more fire, more soot, more carbon injection, more feedback. In other areas, you get heavier rains and erosion, washing soils into rivers. Those rivers carry nutrients into seas, causing algal blooms. When blooms die, they decay, consuming oxygen, expanding dead zones. So, the land and ocean are connected, and the eruptions tug on both. You start to feel the planet as one coupled system, not separate scenes. A fissure eruption in India can contribute to dead zones in distant seas, not instantly, but through repeated atmospheric and oceanic adjustments. That is what makes flood basalt provinces candidates for global crises. Not because any single flow is world-ending, because repetition becomes planetary. Now you take a step back and look at the evidence humans will later use. You do not get to look at the Deccan with your eyes anymore. You have to look at it with instruments and arguments and mud on your boots. You trade the warm hillside for a lab bench, and the romance dies immediately. But the planet leaves fingerprints even when it tries to pretend it was innocent. You start with the simplest trick. You drill down through the stack. You pull up cylinders of basalt, one after another, like dark candles. You expect sameness because basalt looks like basalt to tired human eyes. But under a microscope, each flow has its own small betrayals, tiny crystals that grew faster or slower, glass that formed where cooling panicked, bubbles that froze at different depths, telling you how much gas was trying to leave. You scrape a red bowl seam, and it powders into clay. That clay holds iron oxides and weathering minerals, and sometimes plant traces. It is a pause you can weigh in your hand. You run your fingers through it, and it stains your skin like rust. This is not lava anymore. This is the planet trying to heal between wounds. Now, you do the part humans love. You date things. Not with calendars, but with isotopes, the slow-ticking atoms in minerals. Argon in basalt is your favorite liar because it can be trapped or lost or reset. So you do it carefully, flow by flow, layer by layer. You look for the youngest flows and the oldest ones to bracket the madness. And what you find is pacing that is both comforting and worse. The whole province did not erupt in one apocalyptic weekend. It came in episodes, pulses that could cluster. Big outputs in short geological bursts with quieter stretches between them. Quieter does not mean safe. It just means less obvious. Because the plumbing stays hot and the gases can still seep. Now you widen your evidence net because rocks alone are never enough. You walk to ocean sediments far from India where the seafloor kept diaries. Thin layers of mud falling year after year, stacking like sleepy snowfall. In those layers, you look for mercury. Not because mercury is poetic, but because volcanoes leak it. Mercury rides the wind, settles into oceans, and gets locked into sediment. A mercury spike is like a smoke alarm in the geologic record. It does not tell you where the fire was, but it tells you something burned. So you line up those spikes with the timing of Deccan pulses, and you keep finding the same uncomfortable overlap. Elevated mercury around the end of the Cretaceous. Not a single blip, but a sustained pattern that whispers, this was not quiet. Now you look at carbon isotopes, the planet's mood ring. When the carbon cycle gets disrupted, the isotopic ratio shifts. It is not magic, it is accounting. Light carbon can mean organic burial, or methane release, or stressed productivity. Heavy carbon can mean different balances of photosynthesis and decay. Either way, it tells you the system was being shoved. You line up those isotope wiggles with Deccan timing, and you feel the push. A long, messy perturbation, not a clean line. You are not proving one cause. You are proving stress. And stress is what matters, because stress lowers the threshold for collapse. Now you have to make a decision. Do you believe the Deccan was a steady simmer or a set of sharp kicks? Because a steady simmer gives ecosystems time to inch along. Sharp kicks are what snap bones, so you look closer at the flow stack itself, at the thickness patterns, at the distribution, at the way some formations pile up. You notice that a large portion of the volume may have erupted in a relatively tight window. Not instant, but tight enough to matter for climate. It is the difference between a slow leak and a burst pipe. And you already know what burst pipes do. They flood the house before you can find the shutoff. Now you go back to the air, because the air is where consequences travel. You picture a single Deccan pulse, a large one, curtains of fire across fissures, and lava pouring in sheets. Now you add the part people forget, the intrusive magma. Not all melt reaches daylight. A lot of it stalls in the crust, as sills, as dikes, as bodies that cook rock. That cooking matters. Because Western India had sediments, carbonate rocks, and organic rich layers, and things that behave badly when heated. Bake limestone, and you liberate CO2, bake organic matter, and you can release methane and other carbon compounds. So the Deccan may not have only exhaled mantle gases. It may have also cooked the crust into adding its own fumes. You realize what that means, and you do not like it. The eruption is not just what you see at the surface. It is also what you cannot see, a hidden carbon factory underground. Congratulations, the planet found a way to bill you twice. Now you imagine the late Cretaceous sky again, and it gets thicker, not only with sulfur haze, but with a longer-lived greenhouse load. The oceans, already warm, take on more dissolved carbon. That acidifies surface waters and stresses organisms that build shells, and at the same time, nutrient runoff and circulation changes promote low oxygen zones. So marine ecosystems are being squeezed from multiple sides. Hotter water holds less oxygen, and stratified water resists mixing. It is like putting a lid on a pot, but the pot is the ocean. Now you look at plankton, because plankton are honest witnesses. They respond quickly, and they get buried everywhere. In the sediment record, you see shifts in species composition. Some forms decline, others surge opportunistically. The community becomes simpler, more dominated by survivors that tolerate stress. That is not a victory. That is a warning sign. On land, you see changes too. In pollen, in plant assemblages, forests thin in some regions, and fire indicators rise in others. Everything starts looking like a world that is adapting to repeated punches. You take all this, all these proxies and arguments, and you build a timeline. It is not a perfect timeline, but it is the best one humans can assemble. And the story that emerges is not clean hero and villain. It is a system already wobbling. Then you feel the next pivot approaching, like a vibration under a table. Because while volcanism is repetition, space rocks are punctuation. And punctuation does not care about your slow, careful sentences. You stand on a late Maastrichtian shoreline, looking out over warm seas. The air is heavy, and the seasons have been strange lately. Not apocalyptic every day, just unreliable. Like a climate that keeps changing its mind mid-sentence. You can taste salt and faint sulfur and wet vegetation. You tell yourself, this is survivable. Life has survived worse, and it has. Then, far away, a dot in the sky grows brighter. Not like a star, like a problem. At first, you do not register it, because the sky is full of indifferent light. But this one moves against the background. It is coming in fast, and the atmosphere starts to notice. The object is heating the air ahead of it, compressing it into plasma. A bright streak forms, a second sun that is not rising. You have no context for what you are seeing, because nothing alive does. This is not weather, it is orbital mechanics arriving on schedule. The impact happens far away, across an ocean, at what will be the Yucatan. But distance is not safety, not for a planet-sized shock. The moment it hits, the energy release is obscene. Rock behaves like liquid, ocean becomes vapor, and the crust rings like a bell. The first thing you feel, even in India, is not fire. It is a low shudder, a deep, rolling wave in the ground. Seismic energy travels through the planet, and it does not ask permission. The ground under you, your basalt stack, your fissures and dikes, all of it feels the passing wave. It is like kicking a table that already has a glass trembling on the edge. If the Deccan system was pressurized, this is the kind of disturbance that can matter. You cannot say it triggers everything because geology hates certainty, but you can say it adds stress, and stress opens doors. Now the sky begins to change, and it changes fast. Impact ejecta blasts into the upper atmosphere. Molten droplets and dust spread around the globe. Some of it re-enters, and the re-entry heats the air like a broiler. For a short time, the sky itself radiates heat downward. You do not need lava to start fires now. Forests ignite from above, sparked by heat and lightning and dry debris. Soot rises, darkening the sky further. Then, the darkness arrives for real. Dust and aerosols block sunlight, and day becomes dim. Photosynthesis drops hard, and food webs start starving at the base. This is the impact's signature, sudden and sharp. Now you hold two disasters in your hands, and you have to separate them. The impact does the instant violence, the abrupt winter, the global firestorm patterns. The Deccan does the long exhale, the repeated chemical stress, the drawn-out warming and cooling cycles. One is a hammer blow. One is a slow squeeze. And you, unlucky creature, are living in the overlap. Because the impact does not happen on a stable planet. It happens on a planet already dealing with volcanic mood swings. So recovery is not simply waiting for dust to settle. Recovery is trying to rebuild while the Deccan keeps breathing. You stand in the dim light after the impact, and the world feels hollow. The air is cooler at the surface because sunlight is reduced, but the upper atmosphere can be warmer in strange ways because of absorbed radiation. Rain patterns change again, and now ash and soot feed into clouds. Acid rain becomes a different kind of cocktail, mixing impact-derived compounds with volcanic ones. Oceans cool at the surface, but can become more stratified in complicated ways. Dead zones do not politely vanish because the air is cooler. They can expand if circulation is disrupted. So the biosphere is hit with starvation from darkness and poisoning from chemistry and habitat loss from fires. This is where extinction becomes locked in for many lineages. Not because every individual dies instantly, because the networks that support them collapse. Plants struggle, herbivores starve, predators follow. In the ocean, plankton crash, and everything above them begins to unravel. The survivors are not the strongest. They are the least picky. They are the ones that can eat detritus, hide underground, tolerate heat swings, and reproduce fast. It is not a heroic story. It is a story of stubborn mediocrity. Now you listen for the Deccan again. Because the lava is not done. This is the part that feels wrong in the human brain. You expect a catastrophe to end, to have credits, But flood basalt provinces do not do credits. So you look for evidence that the Deccan tempo changes around the boundary. Some studies suggest eruptive rates increase near the time of impact. Others argue the timing is close but not perfectly synchronized. You can feel the debate, the careful language, the desire not to overclaim. But you can also feel the physical plausibility. Seismic waves can alter stress fields, especially in already fractured crust. They can mobilize magma, open pathways, unclog conduits. Even if they do not create melt, they can help melt move. So you imagine the Deccan plumbing after the impact, trembling, shifting, magma bodies at depth slosh slightly, like water in a shaken container. Cracks that were sealed by mineral growth can be rebroken. Dike tips that were stalled can be encouraged. And on the surface, the ecosystem is so damaged that another pulse matters more than it used to. This is the cruel arithmetic of timing. The same volcanic pulse in a healthy world is a crisis. In a world after impact winter, it is a finishing move. So you watch in your mind as fissures open again. Curtains of fire under a dim sky, lava pouring into a landscape that is already burned and quiet. The lava does not care that the dinosaurs are fading. It spreads anyway, covering ash, covering charcoal, sealing a boundary into stone. And above, the gases add themselves to an atmosphere already confused. SO2 makes haze, but the sky was hazy already. CO2 adds warmth later, but the world is cold now, temporarily. So the climate response becomes layered, like the basalt, short-term darkness and cooling from impact debris, intermittent cooling from volcanic sulfate, long-term warming from volcanic and baked crustal carbon. You have built a climate puzzle that refuses to be solved cleanly. And that is the truth, because Earth is not a courtroom drama. It is a pile of processes happening at once. Now you step forward in time because the boundary has passed. The dust settles slowly over years. Sunlight returns, then at first, then stronger. But the world that sunlight touches is different. The forests are patchier, the animal community simplified. The oceans have lost many specialists, and reefs are wounded. The baseline of life has shifted, and you do not get the old one back. Meanwhile, the Deccan continues, because Mantle heat does not care about extinctions. The Plume, if you want to keep calling it that, keeps delivering melt. The plate keeps moving, and eruptions keep arriving in episodes, writing more basalt over the story. Now you arrive at the part of the Deccan that feels like pure volume. Peak output, repeated sheet flows stacking up into what will become the famous traps. You walk on a fresh basalt plain, and it is still cooling. The surface is dark, matte, and faintly steaming in low spots. It crunches underfoot in places where the crust shattered, making clinker. In other places, it is smooth and ropey, like a frozen river caught mid-swirl. Heat radiates upward in waves you can see in the air. You can smell wet stone and sulfur and the faint metallic odor of new minerals. Now the cooling begins to draw patterns. As the lava interior contracts, it fractures. The fractures start as small cracks, then organize into polygons. Hexagons are common, not because the planet likes geometry, but because it is efficient. Cracks spread in ways that minimize energy, and hexagons win often. So you watch a planet-sized slab of basalt turn into a tiled floor, one slow snap at a time. Columnar jointing forms as the cracks propagate downward. Long columns, straight-sided, like a cathedral built by physics. Congratulations! You have found architecture that does not care if you admire it. You place your hand on a cooling column, and it is warm enough to feel alive. It will stay warm for a long time, because basalt is stubborn about losing heat, especially when it is thick and insulated by its own crust. Now you follow the lava while it is still moving, because movement creates the features people misread later. You walk along a channel, a shallow trench where lava focused its flow. The channel banks are levees of cooled basalt, built up as the edges chilled first. Inside the channel, the lava stays hotter, faster, more fluid. This is how a sheet flow can travel far. It organizes itself into transport corridors. Sometimes the roof closes over, forming a lava tube. A tube is a secret tunnel carrying molten rock under a hardened skin. It is the volcano's way of cheating heat loss. You crouch by a skylight, a spot where the roof collapsed. You look into the tube, and the glow below is steady, like the inside of a furnace. The air that rises is hot and sour, and it dries your throat instantly. You back away because curiosity does not make you fireproof. Now you watch the flow inflate again, because inflation is how you get thick units without a tall pile. The surface crust forms, then molten lava keeps feeding beneath. The crust lifts, sometimes meters, like a slow swelling blister. If the pressure becomes too high, the crust breaks and a new lobe oozes out. So the flow front advances in pulses within pulses. Even a single eruption episode has its own internal rhythm. You start mapping this in your mind because future geologists will. They will trace flow lobes, identify channel systems, find tube networks. They will use these to infer eruption rates and durations. Some flows may have erupted over months to years. Others could last longer, with pauses and reactivations. The point is not the exact number, the point is persistence. This is not a one-day event. It is sustained emplacement. Now you step onto a flow top that is vesicular, spongy. Gas bubbles rose and got trapped near the top as the lava cooled. That makes a porous zone, a natural reservoir layer. Below that, the flow interior is dense and impermeable. So each flow becomes a layered aquifer system waiting for future rain. But right now, those bubbles are also a record of degassing. Each vesicle is a little memory of gas. Trying to leave, some bubbles burst at the surface, releasing their contents. Some stayed sealed, only to be filled later by minerals. That later filling is how you get amygdales, calcite, zeolites, quartz, precipitated by groundwater moving through cooling rock. So even as the province forms, it is already being invaded by water. Rain falls, seeps into cracks, circulates through warm basalt. Hydrothermal systems develop, hot water altering minerals, weakening zones. This is not just interesting, it changes stability. Altered zones can become slip plains, future landslide surfaces. They can also become easier pathways for later intrusions. Again, the system is learning, Now you find a red bowl layer forming in real time, in miniature. A pause between flows, a surface exposed to weathering. The top oxidizes, iron turning red, clays forming, dust settles, organic matter accumulates, small plants colonize. Then the next flow arrives and bakes it. The soil reddens deeper, minerals change, water is driven off. The pause becomes a seam, the seam becomes a marker. You stand on that seam and feel the time it represents. Not long in human terms, maybe decades to centuries to a few thousand years, but long enough for a thin living skin to form and be erased. You begin to understand why the traps look stepped today. Different flows erode differently. Flow tops are rubbly and weak. They weather faster. Flow interiors are massive and strong. They resist longer. So as rivers cut down, they preferentially remove the softer parts. That is why benches form where tough interiors overhang and weaker tops crumble away beneath. You walk along one of those benches and you can feel the basalt's bias in your ankles. It wants to break along its own cooling scars, not along your convenient hiking route. Every joint, every vesicle band, every rubbly top is a pre-written failure line. Water does not need imagination to erode this place. Water just needs time, and the Deccan gives it all the time in the world. Now you look back across the fresh plain in your mind, still young, still warm in pockets. You realize the trap staircase is not built by lava alone. It is built by lava arguing with rain, then losing slowly on schedule. The lava writes the first draft. The monsoon edits it line by line until the terrain becomes readable. And the editing begins almost immediately because the basalt cools fast at the surface. The first rains find cracks, and the cracks welcome them. They seep down into the vesicular tops, then stop at dense interiors. So water spreads sideways, pooling in hidden horizons. You do not see a lake. You see a thin, saturated layer trapped inside stone, like a secret. Congratulations, you are standing on a future aquifer. Not a single underground ocean, but a stack of leaky shelves. Each flow top holds water until it finds a fracture. Each fracture connects to another layer, and the whole plateau becomes a slow sponge. This is why, millions of years later, wells here can be generous or cruel. Hit a vesicular zone, and water rises like relief. Miss it, and you drill into a dense interior that gives you nothing but disappointment. But in the time you are walking through now, those wet layers do something else. They speed up chemical weathering. Basalt minerals do not stay basalt minerals when water and CO2 are present. They start to break down into clays and iron oxides and soft altered zones. The rock literally turns into soil from the inside out, so the newest flows begin weakening before the next ones arrive. And that matters because the province is still erupting. Even during peak volumes, there are pauses long enough for rain to infiltrate, circulate, and change the rock's strength. Long enough for hydrothermal systems to keep working the basalt like a slow fever. Hot water moves through fractures, dissolving, reprecipitating, rearranging minerals. It leaves zeolites in vesicles, and calcite in joints, and altered halos around intrusions. Those halos are weaker than the original basalt, So when later erosion arrives, it does not need to attack fresh rock everywhere. It targets the already softened parts first, and that selective editing is how trap topography becomes sharper with time. You walk to the edge of a cooling flow front, where the surface breaks into jagged clinker. You can feel how fragile it is compared to the dense core behind it. Clinker is basalt that cooled while being churned, broken, and exposed. It has more surface area, more cracks, more places for water to bite. So clinker turns to soil faster. Dense interiors resist longer, standing proud as ledges. Now you understand the future landscape in a mechanical way. A stair step is not an accident. It is a consequence of textures baked into each pulse. And those textures were set by eruption style. Runny pahohio that inflated gives you thick, coherent interiors. Rough that broke itself gives you weak tops. The Deccan is not one uniform rock. It is a repeating pattern of strengths and vulnerabilities. So, while the eruptions are still active in your story, the next chapter is already forming. Rivers begin to choose their routes. At first, they are confused. A new basalt sheet has flattened the old gradients. Drainage that used to flow into a valley now hits a wall of rock. Water ponds, then overtops, then finds a new low point. It cuts a new channel, often along joints and fractures. If you could watch from above, you would see streams tracing the cooling grid. They follow column joints like a city following streets. They exploit dikes too, because dikes can either resist erosion or crumble. A dense dike can become a ridge. An altered dike margin can become a trench. Either way, the intrusion forces the surface to make decisions. And water loves decisions, because decisions create pathways. Now you step forward again, because the province is still pouring itself. Peak volumes mean the surface is repeatedly resurfaced. Rivers are not allowed to mature. They are young again, over and over, reset by new rock. So you get a strange kind of landscape, not ancient, not stable, but repeatedly born. It is a childhood that keeps restarting, and it makes the terrain look deceptively simple. Flat plains, broad sheets, gentle slopes, but underneath the stack grows thicker and heavier and more complicated. The crust beneath this province is being loaded like a barbell. Basalt accumulates and the lithosphere flexes. Where it bends downward, space opens for more magma storage. Where it uplifts at the margins, slopes steepen and future rivers gain power. So the lava is not only making rock, it is sculpting the future hydraulics by changing the tilt of the land. And tilt is everything in erosion. A small tilt, held for millions of years, becomes a canyon. Now you feel the planet's patience returning, even in the middle of catastrophe. The eruptions come in episodes, and each episode has an aftertaste. The aftertaste is heat leading out of thick basalt piles. Heat keeps water moving in the subsurface. It drives convection, pulling cool rainwater down and pushing warm mineral water up. That circulation changes the chemistry of groundwater. It can become rich in dissolved ions, in calcium, magnesium, silica. When it cools or meets air, it deposits minerals, it lines fractures with crystals, and seals some pathways while opening others. So, permeability is not fixed. It evolves. A flow top that was once a great reservoir can get cemented shut. A fracture that was once sealed can reopen when cooling contracts the rock. If you are trying to predict where water will go, you will fail at least once. The Deccan is a moving target, even after it cools. Now you shift your attention to the Western Ghats again, because the escarpment is part of the trap story. The Ghats are not a volcanic ridge like a classic mountain chain. They are a cut edge, an erosional cliff, a retreating boundary. Imagine the basalt plateau as a giant table. Now imagine someone slowly sawing away at one side for tens of millions of years. The saw is rivers and monsoon rain and gravity. The cut edge retreats inland, not smoothly, but in collapses, landslides, and headward erosion. Headward erosion means a river eats backward, upstream, toward the plateau interior. A small stream at the edge cuts a notch. The notch deepens, steepens, then undermines a bench. Blocks detach, fall, and the escarpment moves a little farther inland. It is not dramatic in human time, but in geologic time, it is relentless. The Ghats become the sharp lip where the plateau meets the coastal plain. That lip becomes a climate machine. Moist air from the Arabian Sea rises against it, cools, and drops rain. So the escarpment creates its own punishment. It forces rain to fall on itself, feeding the rivers that will keep cutting it back. Congratulations! The plateau built the wall that invites the storm. Now you drop down, in your mind, to a river that has finally gained permission to carve. It starts as a narrow cut along joints. Then it reaches a weak horizon, a rubbly top, a red bowl seam turned clay. The river undercuts that horizon, and the ledge above loses support. A slab breaks off with a crack you feel in your chest. The river carries the broken basalt away as angular blocks. Those blocks tumble, grind, and become smaller. Over time, they become gravel, then sand, then silt. And now you follow a single grain because this story needs a traveler. You are that grain. You were once part of a dense flow interior, locked tight in black rock. Now you are broken free, scraped by water, knocking against other grains. The river rolls you downstream in floods, then leaves you stranded in dry seasons. Each time you move, your edges round off a little more. Basalt sand is dark, heavy, rich in iron. It settles quickly when water slows. It builds bars and banks that look almost metallic in sunlight, and as it weathers further, it turns into clay. That clay is what people will call black cotton soil. It is famous for being fertile and infamous for being moody. When it is wet, it swells and becomes sticky. When it dries, it cracks into polygons wide enough to swallow a boot. Those cracks are not just surface drama. They are pathways for water to dive deep quickly during the next rains. So the soil itself becomes part of the groundwater recharge system. The Deccan Traps, eroded into clay, become a water storage strategy. And humans, of course, build their lives on strategies they did not design. Now you jump forward in time again, because the lava eventually stops being the active author. The eruptions fade, the plume influence shifts, the plate keeps moving north. India collides with Asia later, raising the Himalaya, changing monsoons again. But the basalt remains, and the monsoon learns to work with it. Rivers organize. The plateau's surface becomes dissected into mesas, valleys, and stepped hills. From above, the traps look like a giant broken staircase leading inland. From the ground, they feel like a series of decisions you did not consent to. Every valley is a cut through multiple flows. Every waterfall is a cliff where a dense interior sits above a weaker horizon. Waterfalls migrate upstream, eating the plateau back. They leave plunge pools that deepen, then collapse, then repeat. So even the scenic parts are demolition in progress. Now you arrive at a human moment, not because humans matter to the basalt, but because humans cannot resist basalt. People settle where water can be found and soil can be worked. Basalt offers both, with conditions. The vesicular zones store groundwater, but only where fractures connect them. The clay soils are fertile, but they behave like a temperamental sponge. So agriculture thrives here, and also suffers here. You can grow cotton, sugarcane, grains, depending on rain. But you can also watch a field crack open in drought, then turn to paste in flood. The same mineral richness that feeds crops also makes engineering complicated. Clay that swells can push foundations, buckle roads, and warp canals. So you build, you repair, you rebuild. The Deccan is patient, and it charges maintenance fees. Now you walk, in the present, along a modern road, cut again. You see the same flow interiors and tops, but now there are drill marks, concrete, and rebar. People cut into basalt because it is strong. They anchor bridges to it. They place dam abutments against it. They quarry it for construction stone. They treat it like reliable bedrock. And sometimes it is. But basalt is reliable the way an old building is reliable. It holds up until you find the hidden crack. The cracks are everywhere. Cooling joints, column boundaries, fault reactivations, dike margins. Water seeps into them, and during monsoon it pressurizes them. If a slope has a weak clay seam, a red bowl layer, it can act like grease. Rain saturates the clay, reduces friction, and the bench above can slide. A landslide does not need an earthquake here. It just needs a long enough rain and a tired slope, so a beautiful stepped hillside can suddenly rearrange itself. And the debris will look like broken stairs at the bottom of a hill. Congratulations, you have discovered that trap topography can collapse like cheap shelving. Now follow a different human decision, the dam. Basalt plateaus have narrow gorges where rivers cut down through stacks. Those gorges look like natural dam sites. Hard rock walls, confined channels, good for reservoirs. So people build dams, storing monsoon water for dry seasons. They rely on basalt's strength, and they fear basalt's leaks, because joints and vesicular layers can allow seepage under a dam. So engineers grout fractures, drill curtains, and inject cement into rock. They try to make the plateau less like a sponge. Sometimes it works. Sometimes water finds a deeper pathway because water is older than engineering. Now you sit quietly beside a reservoir and you think about what the basalt has become. It started as a killing floor, a repeated burial ground. Now it is infrastructure. It holds water, grows crops, supports cities. That transformation is not redemption. It is time doing what time does. It takes catastrophe and turns it into normal. And normal is always temporary because the basalt is still being edited. Rivers keep carving. Escarpments keep retreating. Groundwater keeps dissolving and depositing. So the Deccan is not a fossil in the way people imagine fossils. It is not a dead thing preserved. It is an active landscape built from dead events. Now you return to the unresolved question you have been avoiding because it never stopped waiting. How much of the end Cretaceous collapse belongs to Deccan timing? And how much belongs to the impact? You can feel the desire for a simple answer. Humans love clean villains, but geology does not do courtroom confessions. It does overlapping mechanisms, partial signals, and arguments that last decades. So you hold the evidence again, not as a verdict, but as a map of possibilities. Deccan eruptions release CO2 and sulfur. They can drive warming, acid rain, ocean acidification, and short cooling pulses. They can also cook sediments, adding more carbon to the atmosphere. The impact delivers sudden darkness, global wildfires, and abrupt collapse of photosynthesis. Those are different weapons, but they can be used on the same victim. A stressed biosphere, already adapting to oscillating climate, has less resilience. So when the impact arrives, the fall is steeper. Then, if Deccan pulses continue strongly afterward, recovery is slower. You can see that logic in survival patterns. Some groups that can hide, burrow, or eat detritus make it through. Some that need stable food chains do not. In the ocean, some plankton recover, but the community is reshaped. Reefs take a long time to rebuild, so the extinction boundary becomes a reset, not a pause. Now you walk along an outcrop where the boundary is recorded indirectly, not as a single line in basalt, but as changes in sediments elsewhere. You picture the iridium spike from the impact, rare metal from space. You picture soot layers from global fires. You picture mercury spikes that may track volcanism. You picture carbon isotope excursions that track a broken carbon cycle. All of these are thin, subtle signals in layered mud. And you try to align them with Deccan pulses. That alignment is hard because dating errors exist, because eruption episodes are not perfectly synchronous everywhere, because sedimentation rates vary, because the planet does not label its layers for you. So scientists argue about sequencing. Did the biggest Deccan outpourings happen just before the boundary? Or just after? Did the impact trigger an increase in eruption rate? Or was it coincidence? Did Deccan warming precede the impact winter in a way that mattered? Did sulfate cooling mass greenhouse warming temporarily, then release it later? You can hear the debate like distant thunder, but you can also feel what is not debated. The Deccan is big enough to matter. The impact is big enough to matter, and the combination is not kind. Now you come back to the traps as a physical place again, because the basalt does not care about debates. It sits under the sun, absorbing heat during the day, releasing it at night. It shapes local climate slightly because dark rock warms easily. It influences vegetation patterns. It influences where water stays near the surface. You walk through a dry season afternoon, and the basalt radiates heat back at you. The air above it shimmers. In low spots, black soil cracks open, making sharp-edged polygons. You step over cracks and feel how deep they go. They are like open mouths, waiting for rain. Then monsoon arrives, and those cracks close. The soil swells, sealing the surface, causing runoff. So you get flashier floods, faster stream response. That can deepen channels quickly during storms. So the same soil that stores water also promotes erosion in bursts. Another contradiction, another trap. Now you follow a river during monsoon. It is brown, loud, carrying sediment like it is in a hurry. It drops boulders in rapids, then picks them up again in bigger floods. It undercuts basalt benches, collapses blocks, and chews them down. At a waterfall, you feel the spray cool your face. You watch the water hit a plunge pool, rotating stones like grinding teeth. That pool deepens until the ledge above is unsupported. Then a chunk of basalt breaks, and the waterfall jumps upstream. So the river is walking backward, step by step, eating the plateau. This is how gorges widen. This is how the escarpment retreats, not with one grand collapse, but with countless small structural failures. Now you notice something else. Humans tend to miss. Basalt weathers into clays, but it also releases dissolved ions. Those ions travel in rivers to the ocean. Over long times, basalt weathering can draw down atmospheric CO2 because chemical weathering consumes carbon dioxide when it forms bicarbonate. So a flood basalt province, after it stops erupting, can become a carbon sink. It can slowly undo some of the greenhouse loading that eruptions added. This is not a happy ending. It is just another loop. Earth breaks the atmosphere, then Earth repairs it slowly, with rain and rock. The repair takes millions of years, and it does not bring back the species that vanished. It only resets conditions for whatever comes next. You stand on a basalt bench at dusk again, in the present. The sky is soft, and the rock is quiet. If you did not know the story, you would call it peaceful. But now you can read the textures like a confession. The columns tell you cooling was slow enough to organize. The vesicles tell you gas was present, trying to escape. The red bulls tell you pauses existed, long enough for weathering. The dikes tell you the crust was repeatedly forced open. The staircase tells you erosion has been working ever since. Everything here is motion, just slowed down. Now you make a choice because this story cannot stay broad forever. You choose to trace water downward into the basalt stack, the way a raindrop would. You let yourself become that raindrop. You fall onto a trap bench during the first heavy monsoon rain. You strike black soil, and for a moment you sit on the surface. Then you find a crack. You slip into it quickly because the clay opened wide in the dry season. You drop past roots, past insects, past the smell of wet earth. Then you reach basalt. You hit a vesicular zone, full of bubbles and pathways. You spread sideways because the dense interior below you refuses to let you pass. You join other droplets, and together you form a thin, perched water layer. You move slowly now because the rock is tight. You seep along fractures, following joints like corridors. In places, you pick up dissolved minerals. You become slightly alkaline, slightly richer. A small chemical courier. You pass an amygdale filled with calcite, and you understand how it formed. Water, like you once carried ions through here, then dropped them. Now you find a larger fracture, one that cuts down through multiple flows. It might be a